In this screencast, we're going to learn about earthquakes, something that if you've lived your whole life in Korea, you may not have experienced, but if you lived in California or other places, you may have experienced them. And if you go to college in Washington State or California, you might feel some. So let's just learn about them. And I apologize if this is something you already know about. I know this is something that's in the standards I'm supposed to cover for this course, so I'm going to do it. But if you've already learned this, I apologize, but not worth it. It's not a bad thing to hear a second time. Okay, so let's start off with the concept of faults. So a fault is a break in a rock. So here we see a break in the Earth's crust along which movement has occurred. So if I look here, I can tell like this rock here is identical to this one here, except it's moved down a little bit. And so I can say like this one used to be here and so on. So this one used to be here and so on. So a fault is simply a break in Earth's crust along which movement has occurred. And in order to differentiate the three main types of faults, we need a little bit of common vernacular here. So the two terms we need to learn are footwall and hanging wall. So the footwall, I say if this is the plane of the fault, the lower part, the part below the fault is known as the footwall. And one way to remember that is you could walk up it and put your feet on that wall. Okay, so that's the wall that your feet would be on. You know, if this was over here and if this was the fault, if I separate it, you could walk on it with your feet on the footwall. The other side is called the hanging wall. That's the part that's above the footwall, and that's because you could hang off of it if you separate. That's just how I remember it. So if I put these two together, this one here, A, the hanging wall would be above B, which is the footwall. Okay, you'll get used to it if you're not already. Okay, so there's three different types of faults, and they are normal fault, reverse fault, sometimes called a thrust fault, and strike-slip faults, sometimes called a transform fault. Okay, we'll just go with these three terms. And the type of fault is determined by what type of motion there is between the footwall and the hanging wall. So we'll start with a normal fault. So in a normal fault, what we find is the hanging wall has moved down relative to the footwall. All right, so you can see this GIF here. We see it's a pretty good illustration of it here that the hanging wall is moving down relative to the footwall. Now, this occurs as what we call tension force. So this is when the crust is being pulled apart, and usually this is done because of gravitational force, and it results in extension. Afterwards, if you look here, afterwards, this is farther. This has gotten bigger, basically. Okay, so the distance between these trees has increased over time. All right, so it results in extensional force. Now, a reverse fault is just the opposite of that. In this case, the hanging wall has moved up relative to the footwall. And you see here that this tree actually gets closer to this other tree and actually runs over that one there, okay? So this is a result of compressional force, which we'll learn about when we talk about plate tectonics. So when the crust is being pushed together, sometimes these faults are moved in such a way that ones move up, and it results in uplift. So you notice that this ends up higher than it was before. And then the third type is called a strike-slip fault. So in a strike-slip fault, these faults tend to be oriented more vertically rather than obliquely like the others. So sometimes speaking of the hanging wall footwall doesn't necessarily make sense. I mean, sometimes it does. But the main thing is the movement is horizontal. It's not vertical. It's not moving up. It's not moving down. It's moving sideways. And we see this as a result of what we call shear force. And a very famous example of this type of fault, arguably one of the most famous examples in the world, is the San Andreas Fault of California, in which the western part of California is moving northwards relative to the eastern part of California. Now, earthquakes occur along faults. I think you probably knew this. Okay, so but basically what happens is energy builds up. So when you push on something, energy builds up and it builds up and it builds up, and eventually it releases. A great analogy for this is imagine if there was a wooden crate full of, I don't know, heavy things on a floor, a cement floor, and you pushed and nothing happened, and you pushed harder and nothing, and pushed harder and nothing happened. Well, you're storing up energy when you're doing this, all right? And what happens is suddenly there's this release of energy and the crate moves. That's exactly what happens in an earthquake. These forces, whether it be tensional, shear, or compressional, they build up over time, and then they suddenly release all at once. and you get this movement between the foot wall and the head wall, and that's when an earthquake occurs. And it releases energy in the form of seismic waves. And these seismic waves come in two types primarily. There are P waves and there are S waves. We'll examine each of these individually here in a minute, okay? So the focus of an earthquake is basically the point along the fault down underground where the energy was actually released. It's almost like you detonated an explosive at one point. That's where the energy was released. And then directly above it on the Earth's surface is a place we call the epicenter. So because we humans live on the surface of the Earth, not kilometers below the surface, we tend to notice that the earthquake motion tends to be most intense at a certain point on the Earth's surface, and we call it the epicenter. But it's worth noting it is directly above a point down in the ground where the energy was actually released, which is called the focus, or sometimes it's called the hypocenter. Now, in order to measure these seismic waves, we use a device known as a seismograph. Now, this is an old school one. This illustration here, this is what was built, I don't know, maybe over 100 years ago. But it's the same basic concept. So basically, you have a fixed mass, so a large mass has a lot of inertia, doesn't want to move much. And on it, you have a needle that has ink dripping out of it. And you have a drum of paper that's moving around. And so what happens is, if an earthquake happens, the base may move side to side, but because this mass has so much inertia, it just stays in place. And so the table moves underneath it, and you get these wiggles. And that's how we can measure earthquakes. And so what we find is that the seismic waves allow us to interpret how far away an earthquake was and how much energy was released by the earthquake. And so if you recall from the previous screencast, we have P waves and S waves. So the P waves are the back and forth waves, the ones that are able to travel through liquids and solids and gases. And these P waves tend to travel faster, whereas S waves tend to travel slower. And so we find then is the P waves, and P stands for primary actually, although it's also push-pull, okay? They arrive first, and then they're followed later. So in this case, these are 1 minute intervals. So like a minute goes by, 2 minutes, 3 minutes, 4 minutes, 5 minutes goes by, and now the S waves arrive. Now remember, the S waves are, S stands for shear waves, but also secondary waves. So they come in, actually I got that backwards. This is called primary and secondary, but also push-pull and shear. Okay, and so the difference in these arrival times is going to be crucial and figure out where the earthquake occurred. Now, I'm just going to point this out here. There's no text to support this in this presentation. Sorry about that. But surface waves are what we tend to feel mostly. Okay, so surface waves are fairly complex things. They're also known as Rayleigh waves. But basically, as these waves pass through, they tend to set their Earth's surface in motion, and then that is what we tend to feel the most. But these don't originate at the focus. These are formed by the interaction of these waves with the surface. Okay, so it's really the P and S waves we're most concerned about. So here's the thing. Since they travel at different speeds, the distance between them, so imagine we have two runners, and one person is faster than the other one. They start at the start line. They're together. As 1 second later, the faster person is a little bit ahead. A minute later, that faster person is considerably ahead. 5 minutes later, that faster person is a lot farther ahead, and so on. So the idea then is when an earthquake occurs, different seismic stations, seismographs around the world will record them. And what they can do is they say, okay, look, here in Juneau, Alaska, we said, well, here's when the P waves occurred. We met them here. And then like 1 minute, 2 minutes, 3 minutes, 4 minutes later, the S waves arrived. And because we know how fast P waves travel, how fast S waves travel, we can interpret that as a certain distance. You'll do a lab with that, okay? But now in Knoxville, Tennessee, here, which is farther away from the epicenter, look what happened. First of all, it took more time for this P wave to reach it because it was farther from the epicenter to start with. But here's what happened, okay? 1 minute, 2 minute, 3 minute, 4 minute, 5 minutes. It took an extra minute for the S waves to arrive. And in this case here, Honolulu is even farther away. How do I know? Because it took 1 minute, 2 minute, 3 minute, 4 minute, 5 minute, 6 minutes. All right. So So 4 minutes, 5 minutes, 6 minutes, that difference tells us that this one was closest to the focus and this one was furthest from the focus. And then what we can do is, if we have at least three stations, which we have a planet full of them, so we do, we can basically determine the distance and we say, okay, in Portland, let's just say I know that from Portland it was, I don't know, let's just say 600 kilometers away. Well, it could be anywhere along this perimeter here. Salt Lake City says, yeah, well, for me, it's also 600 kilometers away. So it could be anywhere along that same perimeter. But in Los Angeles, it's like, oh, mine says it's only 400 kilometers away, so it must be somewhere on this perimeter. And where all three of those come closest to intersecting, that's probably where the epicenter is. In fact, it's much more sophisticated. Now you can actually, use more sophisticated math and actually identify where the focus is and know how deep the earthquake was. Because think about this: a deep earthquake is going to cause less damage at the surface than a shallow earthquake will. Now, you've probably heard of the Richter scale. So the Richter scale is how we measure the magnitude, so the amount of energy released by the earthquake. And so it is just a way of saying how much energy was released. And so earthquakes are fairly common. We'll learn in an upcoming lesson. There's every minute of every day, there's thousands of these really small ones that are 2 or less. They happen all over the planet all the time. No one even feels these. Okay, if you get something that's like between a 2 and a 3, people near the epicenter are going to notice it. Not going to maybe make a little bit of rattling. You notice it. Okay, uh, but then as it gets bigger and bigger, you get up to like between 4 and 5. Some small things might get moved around. You get between a 5 and a 6, and you know what? We start having some mild damage and maybe like some poor constructions or damage, and then we get like a strong earthquake would be something in the 6s and 7s, and these can cause pretty significant damage. And then if you get things between 8 and 9, or even above 9, which happens very rarely, these things are devastating. Fortunately, these happen very, very rarely, and when they do, they typically don't happen very close to people. But they have the potential. The place where my home is in Washington State is along a fault that can have, there's geologic evidence indicating there have been magnitude 9 earthquakes there in the past. And if that was to happen, there's no way my house would survive. But the good news is that they happen so rarely, it's unlikely to happen in my lifetime. Now, the Richter scale is logarithmic, meaning that as you go up it, when you go from a 1 to a 2, you're getting 10 times bigger. When you go from a 2 to a 3, you're getting 10 times bigger. So when you go from a 1 to a 3, you're getting 100 times bigger. So here, magnitude 4 earthquake is 10 times bigger than a magnitude 3, whereas a magnitude 5 earthquake would be 100 times. So 10 times 10, 100 times bigger than a magnitude 3 earthquake. And this is a measure of how much energy is released. All right, so you can almost think of it like the megatons of an atomic bomb, which, by the way, atomic bombs show up on Richter scales. So it's worth noting that modern buildings in most parts of the world are designed so that they can withstand, at least in the developed world, so they can withstand even very powerful earthquakes, especially if it's, and we'll see in a future lesson how to know where earthquakes are likely to happen. They're very unlikely to happen in Korea. But seismic codes are such that most modern buildings will remain standing even in a magnitude 8 or higher earthquake. What won't necessarily stay is the windows might pop out and fall down. The facade, like the bricks on the outside or the marble on the outside, might fall off. So it's a terrible idea to be outside of a building during an earthquake. Unfortunately, when earthquakes happen, people tend to panic. It's very natural to just panic when one happens. And the first thing you want to do is get the heck out of a building. It's just instinctive. And don't do it, because outside the building, there's all this stuff falling down. All right, you just can't prevent that. That we can't have codes that keep windows from popping out and bricks from falling down. We can keep the buildings upright. So you need to stay in the building. But there's still stuff in the building that might fall down on you. You're in a gym, like the basketball thing might fall down. So what you need to do then is the best way to protect yourself from an earthquake is not to run out of the building, is to get under a fairly significant piece of furniture and use it as a shield. So you climb under a table and you grab hold of the legs if you can and just hold on to it as it bounces around. And that way, if things fall down from the ceiling, you're protected from them, hopefully, especially your head, if nothing else. It is worth noting, though, that in order for this to work, for these buildings to remain upright, they need to be built into bedrock. If they're not, if they're built into what's called fill dirt or unconsolidated soils, then what happens is during that shaking, very powerful shaking, the grains of soil become so loose, they start acting as though they were a fluid. They start moving past each other, in which case the buildings tend to fall over. So when you do see significant damage, it's usually because the buildings were not built into the bedrock, or they just weren't built with appropriate codes. And unfortunately, you do sometimes see this in countries that are developing nations. Now, another thing to know about earthquakes is they can cause tsunamis. So a tsunami occurs anytime there is a rapid, large-scale displacement of seawater. Okay, now they can happen in four different ways, and earthquakes is one of them. So in an earthquake, you can have a sudden shift in a fault, and when that happens, you suddenly have a displacement of a lot of water, and this wave will travel outward from it. So another word for tsunamis is seismic sea wave. But it's worth noting there are other ways they can form. One of the most powerful tsunamis that ever happened in modern times was actually the result of the Krakatoa eruption. So volcanic eruptions are known for making tsunamis. I think there was one recently that happened in Indonesia a couple years ago that happened. There was like a musical performance that was happening out on the beach, and it washed away people from the band. It was quite terrible. Uh, Tsunamis can also happen when there's meteor impacts. So, when large things hit the ocean, they displace water. Like so, when the dinosaurs died, it is good evidence that it landed in the ocean and it made very, very significant tsunamis. And then they can happen as landslides. And one that's kind of creepy is the Canary Islands, which are volcanic islands off the coast of Africa. Uh, there is a fault along one side where it seems very evident that one side of it could slump. And if this one did, when looking at the volume of that thing, it could make a tsunami that was so significant, it could basically wipe out much of New York City and other cities along the East Coast of the United States. Now, again, no one knows if or when this will happen, but the potential is there. We understand how to assess the risks, and the risk is real. Now, a couple things about tsunamis. They may sometimes look, if you look at a video, I'm gonna have to look at a video, they can look at times a lot like a regular wave, but they don't act like a regular waves are made by the wind interacting with the surface of the water. But tsunamis are quite different. So tsunamis in the open ocean tend to be very small, like less than 30 centimeters high, with the tops of the waves can be maybe kilometers apart. Okay, but they travel at ridiculously high speed, at jet speeds. We're talking like 800 plus kilometers an hour in the open ocean. So people in boats in the ocean, they don't even know they've been there. Right? These things go right underneath. It's this high, and it's maybe several hundred kilometers to the next one. And so you just don't notice it. But what happens is as they move into shallower water, they slow down, and as they slow down, they get bigger, and they slow down and they get bigger. And it's worth noting, it's almost never one. There's usually multiples of them, and they can come in and they can be quite complex. But there have been a couple, too, in my lifetime that have been very, very significant. And interestingly, I studied geology, and none of them happened from the time I started geology in 1980 until I think it was 2004. It might have been, I think it was 2004 on Boxing Day, the day after Christmas in Indonesia. There was a terrible one in the Indian Ocean. And then a few years later, there was another one that hit the coast of Japan. Obviously, the Fukushima nuclear disaster was a consequence of that. One thing I want to say is this. And listen, we don't have earthquakes in Korea, and we probably won't ever have a tsunami, but we could, okay? So, because these travel large distance across the ocean, we're not that far from Japan. Although the part of Japan that's likely to have these problems is the other side of Japan from us, the eastern side of Japan, for reasons that we'll learn about. But if one was to happen, or if you were to go someplace like Washington State, where I'm from, we know that they get some tsunamis. Okay, here's what you need to know: the way to survive a tsunami is to evacuate upwards. Do not try to run away from it. That's your instinct says run away from it. Here comes this big wave, but you can't. You cannot outrun these things. They can go kilometers inland, and they move faster than you do. And once it's more than, say, knee deep, you're not going to be able to move much anymore. You're going to be at its mercy. You'll see in a minute. You'll never survive. It's like being in a blender. But all you had to do was climb a tree, climb a telephone pole, run up into a building. Most buildings will withstand it, although not all of them. Climb a cliff. Just do vertical evacuation, and you'll be fine. Try to do horizontal evacuation, and you won't survive. Now, I'm not going to click this because I've been talking to you, but you should take a look at this this video clip I have attached at the end of this. It's a very good National Geographic explanation of the tsunami that hit Japan. Okay, thanks for watching.